A robot just tripled its size, crawled through a gap no rigid machine could fit through, then walked on water. Same robot, same day. This is not CGI or concept art. While the world was focused on making robots stronger, China made one that changes shape, and what it can do will shock you. In Shenzhen, researchers at Southern University of Science and Technology just revealed GrowHR, a soft humanoid that triples its size, crawls, swims, floats, and even walks on water. Meanwhile, Limx Dynamics deployed 18 alley robots that stepped out of shipping crates and marched in formation autonomous LE. In Space Engine AIPM-01 is being prepped as the first robot astronaut. Back on Earth, China opened a massive humanoid joint factory, and companies like Unitree Robotics are shipping thousands of units globally. This is not speculation about the future. This is happening right now. One of the most unusual developments comes from Southern University of Science and Technology in Shenzhen. They unveiled a soft humanoid robot called GrowHR, and it is built around a totally different idea of what a humanoid skeleton should be. Most humanoids today rely on rigid column-like frames. They are strong in straightforward ways and predictable, which engineers prefer. The trade-off is that they do not adapt well to changing environments. Human bodies adapt constantly, and much of that capability comes from how bones function. Bones are not just hard structural elements. They combine multiple functions simultaneously: growth through epiphyseal plates, stiffness through compact bone, impact absorption through cancellous bone, multi-scale internal cavities that keep everything lightweight while maintaining strength. GrowHR attempts to bring that biological bone logic directly into robotics. Instead of building standard rigid skeletons, the team designed bone-inspired growable linkages. Each linkage mixes soft, expandable chambers with tensioned cables and rigid adapters that maintain structural stability. A non-stretchable textile layer adds axial stiffness so the linkage does not balloon randomly during expansion. A synchronous cable system runs through each linkage, ensuring extension happens smoothly and uniformly. The robot can deform intentionally while still holding its shape as if it has coherent internal structure, not like a floppy inflatable toy. The numbers are the part that demands serious attention. The linked structures can extend up to 315% of their original length. The robot can extend its height by 278%, meaning it can nearly triple in height at full stretch. When fully extended, GrowHR reaches approximately 1.36 meters tall. Then it can shrink again, in ways rigid humanoids simply cannot match. It can reduce its height by 36% and its width by 61%, specifically to navigate narrow and low spaces. That capability matters, because in real environments, especially rescue scenarios, the bottleneck is rarely raw strength. The bottleneck is getting through debris, through gaps, through doorways, under collapsed beams, and doing it without getting stuck. GrowHR stays remarkably light while achieving all of this. The complete robot weighs about 4.5 kilograms or 9.9 pounds. Each individual linkage weighs around 350 grams. That lightweight design is a fundamental part of why it can be so mobile and adaptive. The way it moves also defies conventional expectations. It can crawl efficiently, with the team reporting crawling speeds of approximately 112.2 millimeters per minute. That speed is already decent for a soft humanoid platform. But the real breakthrough is how much faster it becomes when the growable linkages and joint motors work together. Coordinated actuation of linkages plus motors enables crawling at a pace over 1,120, 2 times faster than either mechanism alone. Growth-style structural change is not just a gimmick or visual effect. It is a performance amplifier. When paired with motors, the robot moves in ways that neither method can produce independently. Then you encounter the multi-mode capabilities where GrowHR starts sounding almost unreal, yet these are demonstrated capabilities documented in published research. Because the robot is so light, it can float and swim in water. It can walk on water at approximately 16 millimeters per second. With ducted fans or quadrotors attached, it can fly over distances up to several meters. That last capability is crucial to understand correctly. They are not claiming it has built-in jet propulsion systems. They are demonstrating that the platform is light enough that adding ducted fans or a quadrotor system provides an aerial mode. The same humanoid body can switch between ground movement, water movement, and short-range flight depending on what you attach. One platform, multiple operational domains. It also demonstrates strength in ways soft robots usually struggle to achieve. GrowHR can deliver powerful kicks, and the researchers specifically discuss energy storage beyond what rigid robots can accomplish. The system can store energy in its compliant structures and then release it rapidly like a biological spring instead of relying purely on motor torque at the instant of impact. Stability and balance are managed through active control systems and by incorporating carbon fiber telescopic linkages, which implies they are mixing materials strategically to get stiffness exactly when and where they need it. One of the researchers, PhD student Wang Ting at Southern University, explained that the growable bio-inspired robot structure could be especially useful for field rescue missions. Its ability to change shape allows it to squeeze through narrow gaps and adapt to terrain that would stop conventional rigid robots. The work published in Science Advances signals that this is not just a prototype, but a serious new structural direction for robotics. While GrowHR focuses on reshaping a single humanoid body, another major push centers on scaling humanoids as coordinated teams. Deploying one robot is impressive. Deploying an entire fleet autonomously is the real industrial test. That is where Shenzhen-based Limx Dynamics comes in. The company released footage showing 18 of its alley humanoid robots autonomously emerging from shipping crates, standing up, walking in formation, and performing a synchronized routine without human intervention. Limx calls it the world's first practical autonomous deployment of humanoid robots. The demonstration emphasized realistic conditions. 18 robots were packed inside standard shipping containers. When the doors opened, each unit stood up, navigated the tight space without collisions, exited systematically, and moved forward together. Instead of stage lab spacing, the robots operated in confined environments similar to real-world logistics scenarios. Limx attributes this coordination to its operating system KOS, a cognitive OS of agents, which enables shared decision-making, movement planning, and collective control. Rather than functioning as isolated machines, the robots behave as a unified group. KOSA integrates cognition and motion in a single framework. Planning and physical response happen almost simultaneously. The system also incorporates memory, allowing robots to store environmental data and anticipate outcomes. During tasks like stair climbing, sensors feed real-time information into KOSA, which adjusts posture and balance instantly. Earlier, alley demonstrations showed single robots navigating rubble and balancing on one leg. The difference now is scale, coordinated multi-robot autonomy. Communications are evolving too. Ex-Humanoid's Tiancong robot reportedly became the first humanoid to connect directly to a low Earth orbit satellite without ground network support. In a live demonstration, it transmitted visual and movement data via satellite while completing tasks in real time, proving humanoids can operate in remote or disaster-stricken regions where traditional networks fail. China is not developing isolated prototypes. It is building a full humanoid robotics ecosystem at scale.